Lecture 23. We're going to be talking about how gases relate to each other through quantitative relationships, or what we would call gas laws. So, getting into things here, we had this slide in class last time, and we talked about, oops, went one too far there, what happens, or what are the relationships between pressure and temperature and volume and our amount of substance. And so hopefully you remember that if we increase the temperature, our pressure will increase. If we increase the volume, our pressure should decrease. And if we increase the amount of substance, then that means that our pressure is also going to increase. So we know that conceptually now, but how do we basically put numbers to this? How do we make these relationships quantitative? That is something that is interest to us as chemists. And so one of the first relationships we're going to talk about is called Boyle's law. It's the first person to kind of describe the relationship between pressure and volume in this sort of quantitative manner. So as we know, as volume goes up, pressure goes down, and vice versa. And so if we want to make an equation for that, we can say that P1V1 equals P2V2, or we could also say that our pressure is going to be proportional or inversely proportional, 1 over our volume, depending on basically how our pressure changes. So that's all of these things are essentially saying the same thing. One other kind of descriptor that we want to factor in here is that this is assuming that our temperature and our number of moles of something, or just the amount of substance, what this lowercase n represents here, all of those, or both of those in this case, are staying the same. So we're not going to be changing temperature, we're not going to be changing the number of stuff. That allows this relationship between pressure and volume to be true. Okay? Next relationship is Amontane's law, and this person was the first one to describe the relationship between pressure and temperature in a quantitative manner. So, as we've said, as temperature goes up, pressure also goes up, and we can quantify that relationship directly. And so that is to say, as pressure goes up, temperature goes up. They are proportional in that way. We could also say P1 over P2 is equal to T1 over T2. And that's another way that we can quantify or represent those things. Okay. One thing I really like about Amontane's law is that through a pretty simple apparatus here, where he had basically a bulb that could feel pressure and a water bath that he could change the temperature of and measure what pressure changes there were, he was able to basically plot data like this, where as he changed the temperature of the water, he would get different pressure readings. And basically this dotted line represents what would happen if you were to extrapolate that data. So these aren't where measurements were made, but if we get a y equals mx plus b equation from this line that we make here with these data points, we can extrapolate that down to where our pressure would be 0. So if we had 0, and what we find is that that is basically absolute 0. So in case you don't remember, the difference between Celsius and Kelvin is 273 degrees. And so Kelvin is a common measurement of temperature because it gives us an absolute scale. So about negative 270 is what he got here. We now know with some more accurate measurements that the actual value is negative 273.15 degrees Celsius is equal to 0 Kelvin. Okay? So just a nice piece of history there that is a pretty simple experiment showing some really impressive measurement of physical properties. Okay? We also have Charles, and Charles was the first scientist that described the relationship between volume and temperature in that quantitative manner. And I think another kind of fun historical fact here is that this work was inspired by hot air balloons. So he was doing this around the time hot air balloons were invented. And he, of course, noticed that if you put hot air into a hot air balloon, it rises. And so he wanted to try and kind of quantify that relationship between volume and temperature. And so that is going to be that as volume goes down, temperature would go down, and vice versa. And that is to say that volume and temperature are directly proportional, and that is, again, keeping pressure and our amount of substance the same. And then if we keep these relationships going, we have Gay-Lussac and Avogadro, the same Avogadro who has a number, also combined observations about these gases related to the volume and the number of things, which generally we're speaking about molecules, and those also have a quantitative relationship. And so the way they did this was, and what might be easy to picture is thinking about if we had a syringe and we plugged the end of the syringe and we tried to press down on the plunger here, we could go so far, but at a certain point we're going to compress all that we can. And that's because we have gases within the syringe still. And so when we push on them, we can actually make measurements about the changes in volume. And if we know the number of things in there, we can relate them. And so that is to say that volume and the number of things are going to be proportional as long as temperature and pressure are constant. So I've thrown a lot of these relationships at you. What is beautiful is that we can actually combine them all into one single equation. And so this is called the ideal gas law. It's shown right here, where our pressure and our volume, P and V, are equal to the number of moles of something as N. And then R is the ideal gas constant that we'll talk about here in a moment. And T is our temperature in Kelvin. So one thing I want to point out, in order for this equation to work, we have to be in the correct units of everything. So pressure has to be in ATM, or atmospheres. Volume has to be in liters. N has to be in the number of moles. Temperature has to be in Kelvin. And then R, our ideal gas constant, has a value of 0.08206. And that is going to be units then on the ideal gas constant of liter ATM divided by moles times Kelvin. Okay? And so we're going to do a lot of practice in class with this that kind of shows the relationship between all of these different gas properties. And the reason it is called the ideal gas law, beyond being just really handy, is that in order for gases to behave ideally, it is an assumption that we make, and it assumes that the gases behave like hard spheres that have fully elastic collisions. So that is to say that the gases do not lose energy when they run into each other, and they also don't stick together. So it might help you, if you've ever played billiards, to think about billiard balls bouncing off one another, basically an ideal version of that. Okay? That's all we're going to talk about in the pre-lecture. I hope that sets you up well for class. We're going to be doing a lot of problems related to our ideal gas law and the quantitative relationships between these different properties. If you have any questions, please let me know. Otherwise, have a great day.